Okay, well, welcome everyone. Looks like we must have a test coming up because I'm here at the kitchen table again, ready to do a practice test. So, haven't done one of these in a while, so it might be a little bit rusty, but I've got sample exam right here, exam number 1 for Chem 152. A copy of this exam will be posted on Moodle somewhere. So if you haven't gone through and done your practice run through the exam yet, I would highly recommend you do that before watching the solutions. That'll give you a good indication of kind of where you stand with regard to the material heading into the test. If you just watch the solutions, that's not quite as good of an evaluation as actually trying the test first. So if you need to, go ahead and pause, try the first question here, and then if you need to, you can check your answer or kind of watch me go through the solution. So jumping into the first problem here, we're given a mass. So we've got a 0.140 gram sample of this compound. There's some chromiums in there, some ammonias, NH3, would be bonded to the chromium or attached somehow to the chromium. And there's a chlorine in there. And this compound was dissolved in water, 250 milliliter solution, and we're given the temperature here as well. And then what we're told is the osmotic pressure was experimentally determined to be 119 millimeters of mercury. And we want to figure out how many ions are obtained from each formula unit when the compound is dissolved in water. So this is not an unusual type of thing for this type of compound with a transition metal. Chlorine can actually attach to transition metal in 2 basic ways. One is through sort of a shared bond, right? It's a polar bond, certainly, with a metal and a chlorine, but if they share electrons, there's actually a physical bond between the two of shared electrons. But this could also be more of an ionic interaction, where there's a positive charge on the chromium and some of the other things attached to it, and the chloride is there as an anion. Now, if it's an anion, those will generally separate when they dissolve in water, but if it's a bond between the metal and the chlorine, they won't separate. So we're kind of trying to determine that. Is this going to stay as one piece, or is it going to break up into 2 pieces when this goes into solution? That basically means we are doing a Hof Factor problem. We're trying to figure out how many particles are produced when this material dissolves to make a solution. And the way we will do that is by comparing what we would call the theoretical osmotic pressure, whatever the colligative property is, osmotic pressure here. We're going to compare the theoretical osmotic pressure, which is going to be based on the concentration of the solution, right? Molarity specifically for osmotic pressure. We want to compare that to this observed osmotic pressure, because if we're getting more than one piece per formula unit, we'll observe a greater pressure change than we might calculate, right? So for osmotic pressure, that's symbolized by capital pi. That's equal to the molarity times the gas constant times the temperature. Right now, in some cases, this is just a C for concentration, right? But the concentration we need to use here based on the units in gas constant will be molarity-based concentration units. But you will see it both ways, CRT or MRT. So we've got R, it's given there in the problem, and it will be on the test too. I will give you the value of R, although probably at this point, you've memorized R. We've got the temperature here too. It's 25 degrees C. Now we will need to convert that to Kelvin, but that can come a little bit later. What we really need here to figure out what the theoretical osmotic pressure here is the molarity of this system. So we've got the mass of our sample, we've got the volume, we've got the pieces to calculate molarity, but let's go ahead and calculate it. Right, so to get to, I missed the letter there, molarity. To get to molarity, we'll take our mass here, 0.140 grams, right? And the formula is up here. We'll need the molar mass of that compound. So let me try to do that over here on the side. We've got a chromium. There's 5 ammonias in there, so that'll be 5 nitrogens and 15 hydrogens, and then a chlorine. So we go to the periodic table, and of course when we take the exam you'll have access to a periodic table. And I have one that I can look at right here. I don't have all of these memorized. Chromium is 52.00. 5 nitrogens would be 5 times 14.01. Hydrogen, there's 15 of them, times 1.01. And chlorine is 35.45. And we need to add all of that together. Right? And I've kind of prepped a little. I've done that ahead of time so that I don't waste some time punching things into the calculator that I don't need to. Kind of making the assumption you know how to use your calculator. Add all that up, we get 172.65. Now, units there, of course, in molar mass is grams per mole. So if we start with 0.140 grams of our compound, 1 mole of that compound, the solute here, would weigh 172.65 grams. That would cancel out grams. That gives us moles. That's part of what we need for molarity. So let's do that one here on the calculator. 0.14 divided by 172.65. And we'll keep a few extra figures here, so we don't want to round too much. So 8.109. Right, this is really 3 sig figs. I'll keep a fourth here till we get to the end of the problem. Then I'll make sure to round to whatever the limiting number is. Looks like it'll probably be 3 for this problem. So 8.109 times 10 to the minus 4th moles of our chromium compound. Now that's part of what we need for molarity. The other piece we need is the volume. And we're given the total volume of the solution was going to be 250 milliliters. If we divide by that, but changed into liters, that gives us molarity. So there's 1,000 milliliters in a liter, so that would just be moving the decimal 3 places. So 250 milliliters is 0.2500 liters, that being a 4 significant figure volume. So if we take our previous answer here and divide by 0.25, that gives us our molarity. So the molarity of our solution is 3.244 times 10 to the minus 3rd moles per liter. Okay. Now we can plug that in back here to calculate what the osmotic pressure should be here. So let's do that. 3.244 times 10 to the minus 4th moles per liter times our gas constant, 0.0821 liter atmospheres per Kelvin moles. Now, if you weren't sure about how to do the temperature, your units here in your gas constant should alert you to the fact that we can't use degrees Celsius. It's not going to cancel out. This, in fact, needs to be the Kelvin temperature. So if I change 25 degrees C into Kelvin by adding 273, that's 298 Kelvin. Right now, moles is going to cancel out here. Liters is going to cancel out here. And Kelvin's going to cancel out. We'll be left with atmospheres. So this will give us the osmotic pressure in atmospheres. Now I've got that already in the calculator as the previous answer. So multiply by 0.0821 and by 298. And I get 0.07936 atmospheres. Right? Now we have to think carefully here. I want to compare this pressure to the one given in the problem. The one given in the problem was not in atmospheres, it was in millimeters of mercury. So it might be wise to take this answer, convert it to millimeters of mercury to make that comparison a little more straightforward. There are 760 millimeters of mercury in 1 atmosphere. Now that was also provided in the problem. Generally, I'll provide information like that on the test, but I think this is also one that you probably have used that enough at this point that you probably should know what it is. 60.3 millimeters of mercury would be the osmotic pressure here. So that's the calculated osmotic pressure, or yeah, calculated or theoretical. This is the actual up here. So in terms of the Van Hof factor, it's abbreviated with the lowercase I, right? That is the observed divided by the calculated, right? And the observed should always be larger than the calculated, right? If the observed was smaller than the calculated, that would mean you're getting fewer pieces than how many molecules you added to the solution, which is kind of a strange thing to consider. So if you get this upside down and you get 1/2, you probably just have it flipped the wrong way. So 119 divided by 60.3, I left off the 0.3 there, writing that out, is the Van Hof factor for this particular situation, and it's 1.97, and that means we're getting 1.97 particles, right, for every molecule of this chromium compound. And that means that it is very close to breaking up into two pieces when it goes into solution, which in this case would mean that chlorine is kind of ionically attracted to the cationic chromium. So that ionic interaction is dissolving in water to give us a chloride anion and then a cation based on the chromium attached to the nitrogen. So, but that would really be our answer there, that just shy of 2, right? And again, the value for the Van Hof factor is going to be temperature dependent. Really low concentration, this could approach 2 if the solute is breaking into two pieces. But as the concentration goes up, those separately charged pieces will be closer relative to each other in the solution, and they're more likely to start to interact. So this value would probably drop some if we started to dissolve more of the chromium here in this sample. Okay, we'll stop there. We'll come back with a different video for problem number 2.